Welcome back to the Deep Dive. This is the show where we take a whole heap of complex information and really try to boil it down into something clear, understandable, and, well, genuinely useful.
Exactly. The mission, really, is to give you a shortcut, a way to get properly informed on important topics without, getting totally buried in data.
And today we're diving into something truly fundamental. I mean, foundational stuff in physics. It's a concept that explains so much, from, I don't know, why your coffee cup stays put on the table.
All the way up to the grand orbits of planets. We're talking about Newton's laws of motion.
Newton's laws, right. And these aren't just like dusty old rules in a textbook.
Not at all. They're more like the operating system for reality, you could say. The framework we've used for centuries to understand and predict how things move. And our source material for this, it puts it beautifully, actually. It says, physics is enjoyable. Being a description of the nature around us, physics is our best friend from the day of our existence.
I really like that quote because it's true, isn't it? Physics can feel intimidating, all equations and diagrams.
But at its heart, it's just about understanding the world we live in. And the book we're using as our guide today, it seems perfect for that. It's described as a comprehensive guide for, quote, a receptive mind.
Yeah, and what's great is its approach. It genuinely starts from the zero level, as it says. It builds things up step by step, which is, honestly, quite rare and really valuable.
It doesn't just assume you know everything already.
Exactly. And it relies heavily on common day occurrences and examples. That's the key, I think, to making these big ideas feel, well, friendly and enjoyable, as the book puts it. So you're not just learning abstract theory.
You're learning why, a dropped ball falls down, or why you feel pushed back in an accelerating car.
Precisely. And it even mentions that the numbers used in the example problems correspond to real situations, so it keeps things grounded.
That is so important. It means we're connecting the dots between the physics and our actual lived experience. So, okay, let's peel back these layers. Newton's laws. Where do we start? The first law, I presume. That's the logical place. Yes, Newton's first law, also known, of course, as the law of inertia. And tied right into that is this absolutely critical idea of inertial frames of reference.
Okay. The first law itself sounds, well, almost simple on the surface, doesn't it? A body remains at rest or in uniform motion in a straight line unless acted upon by an external force.
It does sound simple, deceptively simple perhaps, because it actually pushes back hard against our everyday intuition.
Yeah, because if I roll a ball, it stops.
Right.
My intuition tells me things naturally want to stop, and you need to keep pushing them to keep them moving. That was the old idea, wasn't it, from Aristotle?
Exactly right. For centuries, that was the dominant thought. Because in our world, you've always got friction, you've got air resistance, all these forces acting that we don't always notice.
They're just part of the background noise.
Right. So Newton's genius, building on Galileo's work, was this incredible conceptual leap. He imagined a perfect world, an idealized situation without those forces. And in that world, if you push the ball,
it would just keep going forever.
Yeah.
Constant speed, straight line.
Precisely. And that reveals the fundamental truth. Motion, uniform motion, is just as natural a state as being at rest. You don't need a force to maintain constant velocity. What you need is an absence of a net external force.
Ah, okay. That's the flip. It's not about what causes motion, it's about what changes motion. So constant speed, or being stopped, means the total force acting on the object is zero.
Exactly. Zero net force. The law puts it very precisely. A particle has zero acceleration, so A equals zero, if and only if the sum of forces, the net force F, acting on it is zero.
That if and only if sounds important, like mathematically rigorous.
It is. It means the two conditions are perfectly linked. Zero acceleration implies zero net force, and zero net force implies zero acceleration. No wiggle room. It's the foundation for analyzing motion. If you see something not accelerating, boom, you know the net force is zero.
Okay, seems clear enough. But then the source throws in this curveball, frames of reference. You mentioned them. Why are they so crucial? How does my viewpoint change whether the first law works or not?
Right, this is where it gets fascinating. A frame of reference is just, well, it's your viewpoint, your coordinate system. It's the perspective from which you, the observer, measure things like position, velocity, acceleration.
Like whether I'm standing on the street corner or inside a moving train?
Exactly. And here's the kicker. Newton's first law, as stated, is only valid in certain frames of reference, not all of them.
So in some viewpoints, the law holds true, FA0 means A0, but in others, it doesn't.
Correct. You could be in a frame where you see an object accelerating even though you know the net force on it is zero. Or Conversely, you might see an object with zero acceleration relative to you, but you know there is a net force acting on it.
Okay, hang on. Give me an example. Like, if I'm on a merry-go-round spinning and I put my bag down, it seems to slide outwards, right? Even though nothing is obviously pushing it outwards from my perspective.
Perfect example. From your perspective on the spinning merry-go-round, the bag accelerates outwards without an apparent outward force. Your frame, the merry-go-round, is accelerating, specifically changing direction constantly. It's what we call a non-inertial frame.
Non-inertial, meaning inertia doesn't quite work as expected.
Essentially, yes. Newton's first law, in its simple form, appears to fail in that frame. You see acceleration without a corresponding net force, according to your observations within that frame. This really highlights that there are special frames, privileged frames, where the law does work perfectly, and those are the inertial frames.
Inertial frames. Okay, so these are the good frames where physics behaves nicely, where F really does mean a zero. The universe's preferred coordinate systems, almost. How do we find them? Or know if we're in one?
Well, the definition is almost circular. An inertial frame is one where Newton's first law holds. But the key relationship is this. If you find one inertial frame, let's call it S.
Okay.
Then any other frame, let's call it S prime, that is moving at a constant velocity relative to S, is also an inertial frame.
Constant velocity. So not speeding up, not slowing down, not changing direction. Just smooth, steady motion relative to the first inertial frame.
Exactly. Or even just stationary relative to it. The crucial thing is zero relative acceleration between the frames.
So if we assume maybe that a frame fixed relative to distant stars is inertial,
That's a very good approximation, yes.
then a spaceship drifting at constant velocity relative to those stars is also an inertial frame.
Correct. And the math supports this. If the acceleration of S prime relative to S is zero, then any acceleration you measure for an object in S will be exactly the same as the acceleration measured for that same object in S prime.
Ah, I see. So if F0 implies a zero in frame S, and the acceleration measured in S prime is the same, then F0 must also imply a zero in S prime. The law transfers perfectly.
Precisely. It carries over.
Now what about us? Here on Earth, Earth is spinning, it's orbiting the sun. That doesn't sound like constant velocity. So strictly speaking, is my lab or my living room not an inertial frame?
Strictly speaking, no, it's not perfectly inertial. Because of the rotation and revolution, it is accelerating. However, for many, many practical purposes in classical physics, we can approximate the Earth's surface as an inertial frame.
Okay, so how good is this approximation? When does it break down?
It's generally a very good approximation. The source gives some guidelines. It holds well for objects bigger than about a micrometer, 10 to 6 meters, moving slower than about a third of the speed of light, 108 meters, primarily under gravitational and electromagnetic forces.
So basically, for almost everything in everyday engineering and mechanics, throwing a ball, building a bridge, designing a car.
Absolutely. For those scales and speeds, the effects of Earth's acceleration are usually negligible. You can confidently use Newton's laws as if you were in a true inertial frame.
But if you were dealing with, say, very long-range ballistics or large-scale weather patterns or maybe something moving near light speed,
then you'd need to account for it. The Coriolis effect, for instance, which affects weather systems and ocean currents, is a direct result of Earth's rotation, of it being a non-inertial frame. And for very high speeds, you'd need Einstein's relativity. But for a huge range of problems, the inertial frame approximation for Earth is perfectly adequate.
okay, that makes sense. Choose the right tool or the right frame for the job.
So let's say we've established our inertial frame, or a good enough approximation. We're ready to use the laws, but the source insists on a critical first step before jumping into system. It says you absolutely must decide the system. What does that involve?
It sounds almost trivial, doesn't it? Just pick the object. But it's fundamentally important, and getting it wrong is a common pitfall. Deciding the system means explicitly identifying the specific object or collection of objects that you are going to apply Newton's laws to.
Okay.
And there's a crucial constraint that comes with this, which simplifies the application enormously. All parts of whatever you define as your system must have the same acceleration. Ah, identical acceleration. Why is that so vital? What happens if I try to treat, say, two things moving differently as one system?
Because Newton's second law, Ethma, relates the net external force on a system to its mass and its acceleration. If different parts of your chosen system have different accelerations, then there isn't a single A for the system. The equation doesn't make sense in that context.
Right, you can't just average the accelerations or something.
No, it doesn't work like that. Let's take an example. Imagine two blocks stacked, A on top of B, and you pull block B sideways. Precisely. In that case, you absolutely cannot treat A plus B as a single system for ESMA. You must analyze them separately.
So you'd have to. Step 1, define block A as the system. Identify all forces acting only on A. Gravity on A, normal force from B on A, friction from B on A. Then apply Finnan in A equals MAAA.
Correct. Then, step 2, define block B as the system. Identify forces only on B, gravity on B, normal force from the ground, the force you're pulling with, the normal force from A pushing down, friction from A acting on B, friction from the ground. Then apply Finnan in A equals MBA.
Wow, okay. That makes the choice of system incredibly important. It dictates which forces are external and which are internal. Like, the friction between A and B is external to A if A is the system, external to B if B is the system.
But internal if you could treat A plus B as the system, but you can only do if they move together.
Got it. So choosing the system is about drawing the right boundary around the part of the problem you want to analyze, making sure everything inside that boundary moves as one.
You've nailed it. It's about strategically isolating the part of the universe you're applying the law to. The source mentions examples like a single block, sure, but also things like two blocks connected by a tight string, meaning they share acceleration, or parts of a rope assumed to be moving together. Careful system definition is step 1.
And speaking of strings and ropes, tension comes up a lot. So Fos goes into detail here. We kind of intuitively know what tension is that pulling force in a rope, but what is it fundamentally?
Right, we often just draw it as an arrow, but the source explains it originates at the molecular level. It's fundamentally an electromagnetic force.
Electromagnetic, like magnets and electricity. How does that work in a string?
Think of a string as made of atoms and molecules linked together by chemical bonds. These bonds are electromagnetic in nature. When you pull on the string, you're slightly stretching these bonds, pulling the atoms a tiny bit further apart than their equilibrium position.
Like tiny springs between the atoms.
Exactly like tiny springs. They resist being stretched. And the collective effect of all these tiny interatomic forces resisting the stretch is what we perceive macroscopically as tension.
That's actually amazing. So it's not just some abstract concept. It's the sum of countless tiny electromagnetic interactions inside the material.
It really is. And the source helps visualize this by asking you to imagine cutting the string at some point a conceptual cross-section.
Okay, slicing the string in my mind.
Now consider the two parts you just created, the upper part and the lower part. At that cut surface, the atoms in the lower part are pulling downwards on the atoms in the upper part. That's an electromagnetic force.
And Newton's third law says
That the upper part must be pulling upwards on the lower part with a force of equal magnitude and opposite direction. Also electromagnetic.
okay, equal and opposite forces across the cut.
Yes, and the magnitude of that pair of forces, the force the lower part exerts on the upper, or the force the upper part exerts on the lower, that common magnitude is the tension in the string at that specific point.
So tension is the magnitude of that internal pulling force across any cross-section.
Precisely. And in an ideal massless string under tension, this value is the same all along the string. It's how the force gets transmitted. So at the bottom end, where the string attaches to a block, the string pulls up on the block pulls down on the string, the magnitude is the tension. At the top, where it attaches to the ceiling, the string pulls down on the ceiling pulls up on the string again, the magnitude is the tension.
It connects everything. That microscopic view makes it much clearer. Okay, so we've got inertial frames where FM works nicely. But we talked about non-inertial frames, like the accelerating car or the merry-go-round, where it seems to bring down. How do physicists handle those situations? Do they just give up on EFMA?
No, they don't give up. They use a very clever, well, some call it a trick, others a technique. They want to keep using the familiar structure of Newton's second law, EFMA, even in these accelerating frames.
But how? If you see acceleration without a force or vice versa.
They introduce extra terms into the force side of the equation. Terms that look and act like forces mathematically, but aren't caused by any physical interaction with another object. These are the pseudo-forces, or sometimes called fictitious forces.
Pseudo-forces, fictitious, so they're not real, like gravity or the pull of a string.
They're not real interaction forces, no. They don't obey Newton's third law. There's no equal and opposite pseudo-force acting back on some other object. They arise purely because the observer's frame of reference is accelerating. They are mathematical adjustments needed to make ESMA appear to work correctly from the non-inertial observer's point of view.
It's like a correction factor you add because your viewpoint itself is moving in a complicated way.
That's a great way to put it. It accounts for the acceleration of the frame. Let's go back to that plumb bob in the accelerating car.
Okay, the weight hanging from the ceiling. Car accelerates forward, bob swings backward relative to the car and hangs at an angle.
Right. An observer outside, on the road, inertial frame, sees the tension in the string pulling the bob both upwards against gravity and forwards, causing it to accelerate along with the car. Simple EFMA.
Makes sense from the outside.
But the observer inside the car sees the bob hanging stationary. Relative to them anyway, it's at rest in their accelerating frame. If they only considered the real forces, gravity pulling down, tension pulling up, and at an angle they'd see an unbalanced horizontal component of tension, yet the bob isn't accelerating horizontally relative to them.
So EFMA doesn't work for them unless...
They invent a force. They say, because my frame, the car, is accelerating forward with acceleration A0, there must be a pseudo-force acting on the bob. The pseudo-force has a magnitude of m times A0, mass of the bob times acceleration of the car, and acts in the direction opposite to the car's acceleration.
So it acts backward on the bob.
Exactly. So the inside observer says, the forces on the bob are gravity down, tension up and forward, and this backward pseudo-force m0. When I add all those vectors up, the net force is 0.
And zero net force is consistent with the zero acceleration they observe relative to the car. It makes the equation balance.
Precisely. It allows them to use the Fen-Net-Atin framework, where 0 in this case relative to the car, by adding this non-interaction force term. It's a mathematical construct that preserves the form of Newton's law in an accelerating frame.
It's quite ingenious, really. Like the feeling of being pushed back in your seat when a car accelerates hard, that's the pseudo-force from the perspective of someone inside the car.
Exactly. Or feeling heavier when an elevator accelerates upwards, or lighter when it accelerates downwards. Those apparent changes in weight are explained by adding pseudo-forces in the accelerating frame of the elevator. It's a powerful tool, but always remember they're artifacts of the chosen frame, not fundamental interactions.
Got it. Real forces versus pseudo-forces. Crucial distinction. Okay, so we've looked at single objects, tension, frames. What about more complex scenarios, like multiple objects interacting? How do we tackle those using Newton's laws?
That's where the real power comes in, analyzing systems, like blocks connected by pulleys or objects pushing against each other. The strategy usually involves breaking the problem down.
Back to deciding the system.
Absolutely. You either treat each interacting object as its own separate system, applying EFMA to each one, or if parts move together with the same acceleration, you might group them into a larger system. A classic and often confusing example is the horse pulling a cart.
Ah, yes, the horse and cart problem. If the horse pulls the cart forward and the cart pulls the horse backward with an equal and opposite force, Newton's third law, how does anything ever move? Don't the forces just cancel out?
That's the apparent paradox, and it traps a lot of people. The key is remembering what object each force acts on. Let's break it down. The horse exerts a forward force on the cart. Let's call it FHSC.
Okay.
The cart exerts a backward force on the horse. Let's call it F(h). Newton's third law tells us these have equal magnitude. F and C equals F(h). But, and this is the crucial point, they act on different objects.
F on C acts on the cart. F(h) acts on the horse.
Exactly.
Yeah.
So they cannot cancel each other out when you're looking at the motion of either the horse or the cart individually. They are an action-reaction pair between the two objects.
Okay, that clears up the cancellation myth. So let's analyze the horse first. What forces make the horse accelerate forward?
Right. System in horse. What forces act on the horse? There's gravity, down, the ground pushing up, normal force. Horizontally, the cart is pulling backwards on the horse, F(h). Critically, the horse pushes backward on the ground with its hooves.
And by Newton's third law, the ground pushes forward on the horse's hooves.
Precisely. Let's call that forward push from the ground, P ground and H. That's the force that actually propels the horse forward. So the net horizontal force on the horse is P ground and H forward minus F(h) backward. If P is greater than F, the horse accelerates.
So the horse moves because the ground pushes it forward harder than the cart pulls it backward. Simple as that when you isolate the horse.
Exactly. Now let's isolate the cart. System E cart. What forces act on the cart?
Okay, gravity down, ground pushing up, normal force, horizontally. The horse is pulling forward on the cart, FH1C.
Yes. And there might also be friction from the ground acting backward on the cart's wheels. Let's call it the friction. So the net horizontal force on the cart is FH(c) forward minus friction backward. If F is greater than F, the cart accelerates.
And since FHC and F(h) have the same magnitude, let's just call it interaction. The horse accelerates if the ground's push is bigger than interaction, and the cart accelerates if interaction is bigger than friction.
You got it. It all makes sense once you meticulously isolate each object and identify only the forces acting on that object. You have to distinguish external forces on your chosen system from internal forces within a larger system.
It really drives home the importance of those free body diagrams physicists are always drawing, isolating the object and drawing all the force vectors acting on it.
They are absolutely essential for complex problems. The source mentions other examples, like blocks hanging over pulleys connected by strings, or objects sliding on inclined planes. The method is always the same. Define your systems carefully. Draw the free body diagrams, identify all forces, gravity, normal, tension, friction, applied forces, and apply Fnet to each system along each coordinate axis.
It's a systematic, powerful approach. Deconstruct the complexity into manageable pieces.
That's the essence of applying Newton's laws.
Wow. Okay, that's been a fantastic journey, really. From inertia and the idea that constant motion's natural, through the crucial concept of frames of reference, both inertial and non-inertial.
Understanding tension as an electromagnetic force, introducing pseudo-forces to handle acceleration.
And finally, tackling complex systems like the horse and cart by carefully defining systems and forces. It really feels like we've built up a solid understanding of this foundational framework.
It truly is the bedrock of classical mechanics, and hopefully going through it this way makes it feel less like abstract rules and more like, as the source suggested, an enjoyable description of the world around us. You start seeing these principles everywhere.
Definitely. It connects the textbook to reality. Now, as always, we want to leave you, our listeners, with something to think about, a bit of a puzzle that builds directly on what we've discussed. This one comes straight from the exercises in the source material, Chapter 5, and it plays beautifully on the ideas of non-inertial frames and relative motion.
Okay, set the scene. Imagine you're back in that train compartment, and there's a plumb bob, a weight on a string hanging from the ceiling.
Got it.
Scenario 1. The train accelerates horizontally, say, forward. We know the plumb bob will swing backward relative to the train and hang at a steady angle to the vertical. That's because of the pseudo-force in the accelerating frame.
Right, we covered that. The backward and annonce force balances the horizontal component of tension.
Okay, now scenario 2. Forget acceleration for a moment. Imagine the train is moving at a perfectly uniform velocity, but it's going up an incline, like up a steady hill.
Constant speed, but uphill.
Yes, and suppose, as it goes up this incline, the plumb bob string also makes an angle with the normal to the ceiling. Let's say, purely hypothetically, it happens to be the exact same angle as it made in scenario 1 when the train was accelerating horizontally.
Huh. So just by looking at the angle of the string inside the compartment, it looks identical in both cases, accelerating horizontally versus moving uniformly up an incline.
That's the question. Can a person inside the compartment tell the difference between these two situations solely by looking at the plumb line? Is the train accelerating horizontally, or is it moving at a constant speed up a hill?
Can they tell? If yes, how? If no, why not? And if the plumb line alone isn't enough, what else might they do or measure inside the compartment to figure out which scenario they're actually in?
It forces you to think carefully about all the forces involved in each case. Real forces like gravity and tension, and potential pseudo-forces, and how they combine to produce the observed angle. What information does the angle give you, and what does it leave out?
That's a brilliant puzzle, a real test of applying these concepts, something for everyone to mull over. Well, thank you for guiding us through that deep dive into Newton's laws. I certainly feel much clearer on them now.
My pleasure. It's fundamental stuff, but always worth revisiting.
Indeed. We hope you enjoyed this exploration and feel a bit more informed about the physics shaping our world. Thanks for joining us on the deep dive, and we'll catch you next time.